Yeah, so welcome to this session, use case 3, Zero Hunger by 2030. We have the pleasure to welcome Markus Hinsche, who has been working on this project for a certain time now. And just before I give him the time and the possibility to introduce himself and start the presentation, I would also say that we would appreciate if you all stay muted, and if you have questions, just post them in the chat during the presentation, and we will collect them there and ask him afterwards. And yeah, then of course you might also unmute yourself. So let's see. I think, yeah, there are still some people onboarding, but if you want to, Markus, you're welcome to share your presentation already and start.
Yeah, thanks, Johanna. So we can try to get set up. Yeah. So. Can you see a screen with the slides?
Yes.
Great. Yes, so I don't know, should we wait a bit longer? Or
no, I think we could start slowly. Yeah, I'm going to check if there's more people coming.
Okay. So, yes. Okay, a second. Okay. Great. Okay. Yes, so yeah, thanks a lot, Johanna, for the introduction. So my name is Markus. I am a software engineer with a strong focus on machine learning. So I work in this project called Child Growth Monitor. I work there as a machine learning engineer. And yes, today I would like to present you what this project is all about. So Child Growth Monitor, I joined this a few months ago, and this is a project done by the Welthungerhilfe, which is a NGO. So it's also similar to the World Food Program that you might know. And yes, so I would like to present this to you. As Johanna said, yeah, if you have any questions, please feel free to put these questions in the chat. And in the end, you will also have the opportunity to to ask your questions in person. So there will be time for that. So cool. Let's start with this goal of zero hunger that Johanna already mentioned. So here you have a plot here, and on the y-axis you see the number of people who are suffering from hunger. And actually, you see that there's a decline. So we have less and less people who are suffering from hunger. But to achieve this goal by having actually zero hunger by 2030, it's not enough. Like we won't manage if we keep doing what we're currently doing. So there will still be people suffering. So the idea of this project now is to find innovative digital solutions to increase that decline actually. So we're more in this green area, and we can actually hopefully get closer to zero hunger by 2030. So let me tell you a little bit more about the context about malnutrition. So malnutrition is a big problem. So here on the slide, you can see, okay, 200 million of children are actually suffering from malnutrition, from hunger. And this leads to 3 million deaths actually per year that are totally preventable. Now, what can we do about this? Yeah. So one thing is we can gather insights about malnutrition. So we can go out and measure people to gather more data about where malnutrition happens. This helps us to then send help to the right places, to the right regions, to the right villages where where we see that there's a lot of malnutrition. So the way this is done currently is that you have these different measurement methods that are used right now. For example, there is this MUAC tape. So this measures the middle upper arm circumference. You have a wooden measuring board that's used in the field to do that. You also have a scale. So there, this is how it's currently measured. And yeah, we saw a couple of problems with that. So first of all, like this wooden measuring board is a bit heavy to carry around. So you have to imagine maybe an old woman taking measurements, and she has to walk from village to village. So she's maybe not able to carry this on her own. So with Corona being around, with the COVID-19 pandemic, this ways of measuring this requires physical contact. So this is also getting more and more difficult. And also to get accurate measurements, we found out that you need 2 people ideally. And so, for example, in this case, with like you want to fix the child, so one person has probably, if the child is still young, one person has to hold the child while another person is taking the measurement. And you also need trained staff to actually know how to measure. And if you don't have these, if you have maybe only one person, you get invalid measurements. So some measurements that are not accurate enough. So we can't access malnutrition very well with that. So you end up with some measurements actually not being valid. And yeah, this is not good, because yeah, the data we're gathering should be as accurate as possible, so we can provide the right help. So yes, now this is the status quo. That's what's currently being done, and now we want to introduce a new way to improve the situation by introducing digital tools. And in our case, the idea is to introduce a smartphone app which can scan a child. So I'll walk you through how this would work. So first of all, the parents or caregivers have to sign a consent form. So they just say, okay, they're fine with their child's data being used. In the next step, the child is being scanned. So there is a person taking a scan, almost like a video of the child. And next step, or actually first we have to understand, so the smartphone is a device which not only has an RGB sensor, but it's like a special device which also has a depth sensor. So for every point that the camera sees, you actually get to know the depth. So you get to know how far is this point away from the camera. So that helps us to get data representation, which is a point cloud. So we kind of know in 3D space how far points are away from the camera. And now this point cloud helps us to train a model on this data that we gathered from the child, and then make a prediction that in the very end will lead to a diagnosis for the child. So in the ideal case, we can say, okay, the child is perfectly healthy. We got the measurement and everything looks fine. The kid can go back to play. But in another case where the child is malnourished or very seriously malnourished, we can, for example, send it directly to a doctor or provide other forms of help. Now, one part that's very important in this whole process here is what does this model do, and how do these predictions work? So I want to focus on that a little bit more by telling you, what the machine learning part here does. So let's consider the example where we want to measure, or we want to predict actually the body height. So body height is one of the things we want to predict. So for that, we collected a lot of scans in the field, And so 40,000 scans, and now the data we collected is actually the smartphone scan, so this kind of video of a child. And on the other hand, we also collected the manual measurements. So what did people measure with a wooden measuring board, with the tape and so on. So we can use this data as a ground truth to learn from. So then we train a machine learning algorithm from this data and this labels. And in the end, what we want to achieve is to bring the mean absolute error down, so make the mean absolute error as small as possible. And the error here is really nothing complicated. It just means that the difference between the actual height and the height of the child that we predicted is as small as possible, so that the machine learning algorithm doesn't make a big error. And the error that humans typically do in this task, it's about 1.2 centimeters. And so this is kind of like our gold standard, where the machine also should be somewhat accurate like that. So one part that's very important is, while on average in the mean, this has to be this has to be accurate for a lot of children, we also don't want that a single child gets a wrong prediction. So this is very important to us, that this system is reliable in a way that by introducing our solution, no single child gets harmed actually. So that we don't have a false negative here just because we're using this new solution now, and this one child would suffer. So now I introduced kind of the machine learning task, and in the next step, I would like to tell you which approaches we tried. How did we approach this problem? How did we try to solve that? So there is a paper called VoxNet, and it's a nice idea to put the point cloud, so this data I told you, the steps data, to put it into a voxel grid. So like a 3-dimensional grid. And the nice thing is about this is you can do similar things as with convolutional neural networks. So you can use conv layers and pooling layers and this kind of things. So it's a nice idea, but it didn't achieve great results because the dimensionality is quite limited. What we tried next is PointNet, which is a neural network architecture designed actually for point clouds, and this gave results around 4 centimeters. So we are able to, this means we are able to predict on average the height of the child with like ±4 centimeter accurately. And then yeah, we also tried a more recent architecture, which includes attention, but also uses the point clouds, and we got the error a little bit more down. But then we had the idea of actually doing something completely different and actually taking the point cloud and transforming this into a depth map. So take this 3-dimensional representation of the data and moving this into a depth map, which is a 2-dimensional thing. So it's, you can think of like an image basically. So we project all these points, all these depth points into a 2-dimensional space, and then for each pixel in this 2-dimensional image, it's actually, okay, how far it is away. It's actually representing some distance. And with this 2-dimensional representation, now we get something really nice. We get a representation which is very suited for things that work really well, which is plain convolutional neural networks. These work very well these days, and these operate on 2-dimensional data. So this worked very well, and we could achieve like a very way smaller error. So our predictions are way more accurate. And then lately we tried another approach where we looked at multiple frames. So for, actually, I told you we're doing the scan, so we're doing kind of like a video. So the idea is to actually combine all these frames that we have in our video and then combine this information and make a one prediction in the end. So this Kaparsi et al. Paper introduces several methods to do this, and we chose the late fusion approach. So this means you take one frame and you put it through a neural network, and it extracts some features. And you do this for other frames as well. And only in the very end, you fuse kind of these extracted features here together to make a single prediction. And this even works a little bit better maybe than the plain CNN. So yeah, we're getting towards the end of the presentation. So let me tell you about the great partners we have. So we're working with it's a challenging project. So actually we need a lot of help. So we're working with some good partners. So Sony, Microsoft, Deutsche Telekom, and a lot of others. One thing that's also worth mentioning is this is an open source project. So you can see all the code and a lot of projects materials. They're freely accessible, and this also provides the opportunity for you or for other fellow data scientists to contribute something. So we're very open for contributions. And yes, it's a very challenging project. So to actually deploy that in the field in a third world country, it's very challenging. So there could be cases where there is no internet, or where it's not clear how to actually scan the child. So there are a lot of challenges that the project has to overcome. So yeah, every kind of help is really appreciated. And yes, this leads me to the end of the presentation. So here I put in some links to contact me, and also to see our open source code. And yes, I think we can move on to any questions or comments from your side then. Thanks a lot.
Thank you very much, Markus Hinsche, for presenting us this very important project that helps to somehow reduce malnutrition of kids in the world. So I would have a first question. What are the main challenges in this project? Is it more like on the data preparation, data collection side, or on the machine learning architecture?
Mm-hmm. Yes, I think both are challenging areas. So data collection is challenging because we actually don't know what data to collect. Yeah, so what is the best way to scan a child? To actually how should a scan be taken so it's in the best format? So you can imagine that the child could be standing or lying, it could be front facing or facing the side or from the back. And this is all things when the project started, the scanning process, the capturing process, the data gathering process, this was not clear. So it's actually it's actually the combination, I would think, of both sides to find out, okay, what is best suited for the machine, for the machine learning algorithm, and then getting this back into the user interface. Also, I see that Tristan is here. So Tristan has worked in this project for way much time than I have. So maybe he's also able to answer some questions.
Someone wrote here, it seems the main feature you're using here is growth height. How do you discount stunting due to malnutrition from genetics? Someone could be small and skinny because of genetics, then being malnourished. What would you answer?
Mm-hmm. So the first comment, I think, was, okay, it's mostly height. So I presented height here, so I put this in the focus just to have an example, but we're also doing the weight and the middle upper arm circumference, which are two more indicators which are very important. So together with the height, we have three things that the WHO, the World Health Organization, promotes or says that you have to have these three things in order to access malnutrition. Now, it might be true that there are some cases where there is something special on, like, okay, a genetic disorder was mentioned. Could be some other things. For example, one leg is missing. Yeah, so we have like a victim of a war situation, for example, and then there are special cases indeed. So it's also some challenge to find out about these. Where are these special cases? Are there any abnormalities?
But as far as I understand, the focus is just to help most of the kids at first, right? And yeah, maybe in a second point, concentrate on these specific cases, right?
Yes.
So
not to maybe harm any single child. So it would be maybe we can't give an accurate prediction, but maybe we can say, okay, this is some data we can't deal with yet. Because in the worst case, it might happen that somebody relies on our prediction, and then actually this one child is not treated correctly. Whereas in the physical setup before, without our tool, people would have known, yeah, people would have measured, and yeah, okay, they see, okay, there's something different going on. There was a leg missing. Okay, we have to treat this differently than all the other children.
Okay, so I see there's still some work to do to get those special cases. I would have another question about the deployment. Is it deployed yet, or how are you planning to deploy it?
Yes, it's deployed in a very, very first version in the field. So yeah, more like a development version, but also a version that where we can gather data. And the idea is to have a somewhat better version at the beginning of next year that can be like the minimum viable product from starting of next year. But it's definitely not something that's very stable and deployed in a lot of areas already. So it's more like in this development and MVP phase.
And the plan would be then that people in the countries or on site go out, take the pictures, even if they are not medical or experts, and then they immediately get the result and then start treating the kid accordingly, or how is that planned?
So yes, so maybe you need the training how to deal with the app, but it's I think you need less training than with the other traditional methods. So it also depends on the region and on the country. So the partner organizations we work with in the countries where this is or will be deployed, it depends heavily on them also. So for example, now this project is going on in India, so we get measurements from India, and there we have to work with our partners to see how are they able to measure how many devices can be out there in the field, how many people do they have to measure. So it also depends on the local context.
So maybe one more question on the machine learning architecture or the algorithm you're using. Do you know any other use case where this algorithm is deployed and used?
Any other use case?
Yeah, but just
there are a couple of other like there are 2 other companies, I think, so and 1 or 2 other NGOs who build something similar. Is that what you mean?
Oh, sorry, I meant like the CNN, the special CNN you mentioned you're using with late fusion and.
I see. Not that I'm aware of, but might be, yeah.
Okay, never mind.
About this a lot. So it's like because I feel like, okay, this is a special problem that tackles this one use case, but maybe there's other things where this also helps. Yeah.
Okay, yeah, that was just out of interest to know what's going on now. And before you were already referring to that besides from height, you're analyzing the arm or the weight. Did I understand correctly that you are already taken this into account during your analysis, or are you only focusing on height right now?
So height and weight.
Both.
Is
Okay.
in the focus. Exactly. Yeah. The middle upper arm circumference is a bit more. Yeah, it's a bit more in the future because it's easy to measure. Yeah, it's not that hard to carry around the tape. But in the end, it would be great to have like a solution which covers all of these. So you only need to do one thing to come with your smartphone and do a scan ideally. Yeah.
Mm-hmm. Great. Is there any other question from the audience? Just feel free to ask or get in contact with Markus to contribute to the project. So yeah, if someone is willing to contribute to the project, how to do that, or in what ways is the contribution appreciated?
Yes, so it depends how much involvement you're looking for, but maybe first it's always good to reach out, so via email or LinkedIn or the way you like, and then exactly. So it could be just very small contributions. So you want to work on some parts of the documentation or of the testing or on the help us with our code. So then you can directly head to GitHub and raise a pull request there. Or maybe you want to make this a hackathon project for yourself or a group, and then we can discuss it. So we can actually get into contact and maybe discuss what are the current challenges that or current tasks where we need help with, and then yes, I think we can just speak about that with whoever is interested.
There's one last question in the chat that I'll just give you the 1 minute answer possibility. Yeah, does your dataset focus on particular groups like low income groups, urban versus rural, etc.?
Oh, I think so, yes. So currently the partner organization in India we're working with, they especially go and measure in areas where they see the potential for malnutrition already. So I think the data set is somewhat biased towards that, and there could be other biases obviously in the data set. So that's something totally to look out for. Yeah. So probably it doesn't work well on white, very well nourished children.
Okay. Okay, so we are close to 12 o'clock. So thank you very much, Markus, for giving us insight into the project.
Yeah, thanks for moderating also, Johanna.
Yeah, you're welcome. And I'm just going to post in the chat the link to the next datalift event. So yeah, that if you want to, you can already put that into your calendar and attend or maybe present your own use case if you want to. So yeah, the next date will be Friday, 29th of January, also at 11 o'clock. So it's like lunch breakout. Yeah, so thank you very much and enjoy the rest of the day and have a great weekend, and hopefully see you again end of January.
Great. Thanks, Johanna.
Okay, thank you, Markus.
Thanks, everybody.
Thank you. Bye-bye.